If I told you that right now, as we speak, a chunk of another solar system is slicing through our own like a ghost on a flyby, you might think I'm talking about science fiction, but 3I/ATLAS is very real. It's only the third confirmed interstellar object we've ever seen, and unlike most comets you've heard of, this one does not belong to the Sun. Its orbit is so extreme that it came from deep interstellar space, and after one brief pass, it's gone forever. What makes it fascinating is not just where it comes from, but how it behaves. In some ways, 3I/ATLAS is comfortingly familiar. It grows a coma, it sheds gas and dust, it sprouts a tail. In other ways, it breaks all the patterns we're used to. Chemically, dynamically, even statistically. It looks like a comet, but it doesn't quite act like one. So in the next few minutes, I want to do three things. First, I'll explain what 3I/ATLAS actually is and how we know it's interstellar. Second, we'll dig into the weird details, the parts that make comet scientists scratch their heads. And finally, we'll talk about the interpretations and the alien probe hype. What's serious science, what's speculation, and what this object really tells us about other planetary systems in our galaxy. When I talk about 3I/ATLAS to students or colleagues, I like to start with the simplest point. This is not just another comet. 3I/ATLAS is only the third confirmed interstellar object we've ever seen pass through our solar system, after 1I Oumuamua in 2017 and 2I Borisov in 2019, IFA plus 1. In other words, it's a piece of another planetary system that has wandered into ours for a brief visit and will never come back. Astronomically speaking, that's like finding a loose brick from a completely different house flying through your living room. The name already encodes a lot. The 3I means third interstellar, our third interstellar visitor, and ATLAS comes from the survey that discovered it. The Asteroid Terrestrial Impact Last Alert System, a NASA-funded network of telescopes designed to look for potentially hazardous objects, NASA Science Plus One. One of those telescopes in Rio Hurtado, Chile, picked up a faint moving smudge in early July 2025. Follow-up observations from other observatories around the world pinned down its orbit, and very quickly it became obvious that this object wasn't bound to the Sun at all. Its orbit is strongly hyperbolic, the eccentricity is greater than 1, which means its path is an open curve. It came from interstellar space, it's cutting through the solar system once, and then it's gone for good. Wikipedia plus Odin. That trajectory is the first big way in which 3I/ATLAS differs from ordinary comets. Typical long-period comets that you may have heard about, say Halley, or the big Great Comet of 2025. C/2024 G3, also discovered by ATLAS, either live in or were kicked in from our own Oort cloud, a vast reservoir of icy bodies loosely bound to the Sun by gravity. Wikipedia plus 1. If you compute their orbits precisely, you find that most of them are still gravitationally tied to the Sun, even if their periods are hundreds of thousands of years. 3I/ATLAS is different. It came in from far outside that reservoir, already moving at tens of kilometers per second relative to the Sun, and even the combined tug of the Sun and the giant planets is nowhere near strong enough to trap it. Reuters plus 1. It's a true passerby. The second major difference is origin story. Ordinary comets are leftovers from the formation of our solar system 4.6 billion years ago. Their ices and dust preserve, more or less, the chemistry and temperature conditions of the early Sun's protoplanetary disk. In contrast, everything we're seeing about 3I/ATLAS tells us it formed in another protoplanetary disk around a different star, perhaps even 6 to 7 billion years ago. IFA plus 1. At some point it was likely ejected, probably by gravitational encounters with giant planets in that system, and has spent eons drifting through the interstellar medium before its orbit happened, by sheer chance, to intersect the tiny volume of space occupied by our solar system. The third difference is how we're studying it, because 3I/ATLAS never comes very close to Earth. Its minimum distance is roughly 1.8 astronomical units, almost twice the Earth-Sun distance. NASA Science +1. It was clear from the beginning that this wasn't going to be a spectacular naked-eye object like 3I/ATLAS never comes very close to Earth. Its minimum distance is roughly 1.8 astronomical units, almost twice the Earth-Sun distance. NASA Science +1. It was clear from the beginning that this wasn't going to be a spectacular naked-eye object like C/2024 G3. In fact, even at peak brightness, it hovers around 10th to 11th magnitude, which is far too faint for the unaided eye and even challenging for small binoculars. Wikipedia. But what we lose in wow factor for backyard observers, we gain in an unprecedented spacecraft campaign. As 3I/ATLAS passed just inside Mars's orbit in late 2025, 3 spacecraft at Mars, Mars Reconnaissance Orbiter MAVEN, and others were in a perfect position to take some of the closest images and ultraviolet measurements of an interstellar comet ever obtained. NASA Science +2 SCI News, Breaking Science News +2 NASA and ESA have also coordinated observations from solar observatories like SOHO and STEREO, and from a suite of ground-based telescopes across the world. NASA Science +2 Европейское космическое агентство +2. That multi-wavelength, multi-platform effort is something we simply didn't have ready for Oumuamua and only partially had for Borisov. Now, in terms of physical properties, 3I/ATLAS looks more comet-like than Oumuamua ever did, but it's still not a run-of-the-mill comet. Spectra and ultraviolet observations show that it does have a classic coma, a fuzzy envelope of gas, and it's outgassing water, producing hydroxyl, OH radicals that have even been detected in radio emission by instruments like the Meerkat Array. Live Science +2 SkyAtNightMagazine.com +2, that sort of OH radio line is a hallmark of an active comet. From its brightness and activity, early estimates suggest a nucleus perhaps on the order of several kilometers across, significantly larger than Oumuamua and comparable to or bigger than 2I Borisov. Reuters +1. But when we compare it to typical comets from our own Oort cloud, we already see some oddities. Its color is unusually blue, implying that much of the brightness is coming from glowing gas rather than dust. Its tail structure and antitail features are more complex than average, and it has shown episodes of rapid brightening and possibly strong non-gravitational forces from jets of gas. Cron +2 Sky and Telescope +2. So chemically and dynamically, it's familiar, but with its own interstellar accent. If you put all of that together, the key message I would give is this. 3I/ATLAS is a comet by behavior, but an alien by origin. It obeys the same basic physics as our comets. Ice sublimates, gas and dust stream out, radiation pressure shapes tails, yet its orbit tells us unequivocally that it doesn't belong to the Sun, and its detailed composition carries a fingerprint of a completely different planetary system. NASA Science +2 IFA +2. The ordinary comets we've studied for decades are like fossils from our own cosmic backyard. 3I/ATLAS is a fossil that drifted in from another neighborhood entirely. That's why astronomers are so excited. Every photon we collect from this faint little visitor is a data point about how planets and comets form elsewhere in the galaxy, and once it leaves, there's no second chance to measure it. If you ask me what is genuinely strange about 3I/ATLAS, I'd say there are 3 layers of weirdness: how it behaves as a comet, what it's made of, and how statistically unlikely its whole story seems to be. None of these on their own scream impossible, but together they make this thing feel like the odd cousin at the family reunion of comets. Let's start with its activity. Dynamically, it's a perfectly respectable interstellar object. Very hyperbolic orbit, fast in and out through the solar system, nothing we can't model with gravity, plus a bit of cometary outgassing. But when we look at how active it is, some numbers raise eyebrows. From photometry and spectroscopy, teams have inferred dust mass loss rates of roughly 0.3 to 4 kilograms per second, and a rotation period of about 16 hours. That doesn't sound wild until you compare it with its size and distance from the Sun. for where it is and how big we think it is, it's overachieving a bit in the activity department. On top of that, its coma, the fuzzy atmosphere around the nucleus, is asymmetric and lopsided. And in some datasets, there is surprisingly little classic dust tail for the amount of gas we know is coming off. One study even notes that the morphology is consistent with relatively large dust grains and an almost stubby tail rather than the long, graceful streamer we expect from a highly active comet. Sky and telescope +1. So it behaves like a comet, but with a slightly odd accent in its dust dynamics. The chemistry is where things really depart from the usual script. For run-of-the-mill solar system comets, water is normally the main volatile. CO2 and CO are present, sometimes abundant, but H2O tends to dominate the gas budget. In 3I/ATLAS, we're seeing the opposite. Spectroscopic analyses indicate a very high CO2 to H2O ratio, on the order of 8:1 in some models, and estimates that water may be only a few percent of the gas mass. Spectroscopy Online +1. That's not just a small tweak, it suggests this thing froze out in a much colder, more CO2-rich environment than the regions where most of our Oort cloud comets formed. From a planetary formation point of view, that's fascinating. It tells us that the ice-line chemistry in its parent system was quite different from that of the early solar system, or at least that this fragment was stored in a particularly extreme niche. On top of the basic gas abundances, there are two especially unusual chemical signatures that have gotten a lot of attention. The first is the detection of hydroxyl OH in radio. The Meerkat array in South Africa picked up absorption features at the classic OH frequencies around 1665 and 1667 MHz, giving us the first proper radio spectrum of an interstellar comet. That's odd not because OH itself is exotic, it's a standard product of water being broken apart by sunlight, but because we so rarely get to see an interstellar object this close to the sun, with a radio telescope of that sensitivity pointed at it. In effect, we're using OH as a tracer of how violently the sun is stripping water off this alien iceberg, and the answer seems to be quite vigorously, despite the overall low water fraction. The second chemical oddity is more controversial. Reports of a strong nickel signal, apparently with little or no accompanying iron. Analyses cited by Avilob and others suggest that 3I/ATLAS may be releasing on the order of grams of nickel per second, and that the gas phase chemistry could favor the formation of nickel tetracarbonyl, a complex nickel carbon monoxide compound that on Earth is usually associated with industrial refining. New York Post. Those claims are still being debated. Other groups are more cautious, because disentangling atomic and molecular lines at these distances is tricky. But if even part of that picture holds up, elevated nickel, unusual metal ratios, complex carbonyl chemistry, then 3I/ATLAS is chemically unlike any comet we've studied in detail. That would imply either a very peculiar differentiation history in its parent body or processing in an environment we don't really have an analog for in our own system. Then there are the optical weirdnesses. Polarimetric measurements, looking at how the scattered light is polarized, indicate what some authors are calling extreme negative polarization, more pronounced than we've seen in any solar system comet, and even different from 2I/Borisov, the previous interstellar comet. The probability of getting such an extreme set of polarization measurements by chance, if 3I/Atlas were drawn from the same dust property distribution as our usual comets, has been estimated at well below 1%. Medium polarization is sensitive to the size, shape, and composition of dust grains, so this hints that the grains in the coma of 3I/ATLAS have an unusual structure. Perhaps more porous aggregates, different refractive indices, or a size distribution skewed in a way we don't typically see. Again, that doesn't make the object unnatural, but it does mark it out as living in the tails of our current models. Finally, there's the statistics and coincidences bucket, which is where people's imaginations tend to run away. For one thing, 3I/ATLAS is big by interstellar standards. Constraints from brightness and activity put the nucleus somewhere in the few hundred-meter to multi-kilometer range, making it roughly Manhattan-sized at the upper end. Most population models we had after Oumuamua and Borisov suggested that objects this large should be extremely rare visitors. Yet here we are with a third interstellar object that's comfortably on the large side. Its incoming direction is also peculiar. Tracing its path backward on the sky, it comes in from near the galactic center in Sagittarius and from the southern celestial hemisphere, almost opposite the solar apex direction where earlier models predicted most interstellar interlopers should appear. That already forces us to revisit our assumptions about how these bodies are ejected from other systems and how they're distributed in the galaxy. On top of that, Loeb has pointed out a low probability alignment between the incoming direction of 3I/ATLAS and the famous WOW radio signal region within about 9 degrees on the sky, corresponding to a nominal chance probability of order 1% or less, medium. That's a fun coincidence, but there's no causal mechanism behind it that we can currently justify physically. So when we say 3I/ATLAS keeps getting weirder, we're not saying it violates physics or that it's clearly artificial. What we mean is that every time we point a new instrument at it, we find it sitting at the edge of our expectations. More CO2 rich and water poor than typical comets. Dust with unusual polarization signatures, gas and dust production rates that are high for its circumstances, chemical hints of odd metal and carbonyl chemistry, and an orbit and size that strain our population models for interstellar debris. None of those alone would force us to rewrite the textbooks, but together they tell us that planetary systems elsewhere in the galaxy can produce icy bodies that are cousins to our comets, not twins, and that our sample of 3 interstellar visitors is already rich enough to show us just how diverse that family can be. When people ask me whether 3I/ATLAS might be an alien spacecraft, I usually say the real story is actually more interesting than that headline. The debate around this object has split into 3 broad camps: the mainstream natural comet view, a small but loud maybe it's technology minority, and then the broader public conversation where those ideas get distorted, amplified, and turned into hype. Let me start with the mainstream scientific interpretation because that's the baseline. From the orbital mechanics alone, everyone agrees 3I/ATLAS is interstellar. Its orbit is strongly hyperbolic, so it comes from outside the solar system and will never return. Where the community has converged over the past few months is that it is, in physical terms, a natural comet from another planetary system. That conclusion rests on several independent lines of evidence. We see a classic coma and tail, we detect gas species like water products and carbon dioxide, and most recently we have the first radio detection of hydroxyl, OH, from an interstellar object. Meerkat in South Africa has measured absorption lines at 1665 and 1667 MHz, exactly where we expect OH produced when sunlight breaks up water ice. Live Science, NASA, and ESA have also released multi-wavelength images. Hubble and Mars orbiting spacecraft see a diffuse, evolving cloud of dust and gas, not a hard, shiny spacecraft. Put together, those data look very much like a volatile, rich, actively sublimating body, just chemically skewed compared to typical solar system comets. Now, the weirdness is real, and that's what opened the door for more exotic speculation. Compared to our comets, 3I/ATLAS seems unusually rich in CO2 and poor in water. Its dust shows extreme negative polarization, and some analyses suggest odd metal ratios like elevated nickel relative to iron. Spectroscopy online. That's plenty to keep comet scientists busy, but planetary scientists have proposed natural explanations. Formation in a colder part of a foreign protoplanetary disk, different processing by cosmic rays over billions of years, or simply that our 3 interstellar objects so far are a biased sample of a very diverse population. The Guardian. In other words, 3I/ATLAS stretches our models, but it doesn't break them. That's why you'll see official summaries from NASA and ESA describe it as a rare interstellar comet with some unusual properties, not as a mystery object defying physics. On the other side, you have Avi Loeb and the maybe artificial narrative. Loeb has made a career in recent years of asking whether odd interstellar objects might be alien technology, starting with Oumuamua. With 3I/ATLAS, he's compiled a list of anomalies: the extreme polarization, the CO2-rich composition, the nickel claims, the unusual incoming direction, even a rough alignment with the region of the historic WOW radio signal on the sky. In public essays and interviews, he phrases things carefully. He'll say that perhaps there is an approximately 40% chance of an artificial origin, or that 3I/ATLAS could be an unfamiliar iceberg or alien technology, and recently he's speculated in the press that it might be releasing Sentinel probes around Jupiter. These statements are deliberately provocative. They keep the door open just enough that people can entertain the idea of a spacecraft while still being hedged enough to claim he's just asking questions. What's important scientifically is that none of the data so far require an engineered explanation. The Meerkat radio detection is a perfect example. The first headlines about a radio signal from an interstellar comet sounded like SETI, but the detailed spectrum is exactly what you expect from OH in a natural coma, and teams have used it to confirm outgassing and measure the comet's velocity, not to decode alien messages. Likewise, other astronomers have gone through Loeb's list of anomalies one by one: chemistry, polarization, dynamics, and shown that each can be matched by reasonable, if sometimes extreme, comet models, or by better understanding of the uncertainties in the measurements. The consensus view is that his argument rests more on stacking low probability curiosities and pattern matching than on a robust physical case for technology. This brings us to the social dynamics and hype. Once you combine a real interstellar visitor, some genuinely unusual data, and a prominent scientist hinting at alien probes, you have the perfect storm for the media. Tech and space sites run headlines asking whether 3I/ATLAS is a city-sized spacecraft, tabloids cherry-pick the most speculative quotes, and social media fills in the rest with talk of encoded messages in the radio spectrum or deliberate targeting of Jupiter. In that public arena, subtle distinctions, like "we've set an upper limit on any artificial transmission," or "this polarization is unusual but not unique," basically vanish. From inside the field, though, the tone is very different. Most comet and planetary scientists see 3I/ATLAS as a fantastic natural laboratory. The OH detection, for instance, is celebrated as the first clear radio signature from an interstellar object, giving us a new window on the distribution of water in the galaxy. Multi-mission campaigns from Hubble, Mars orbiters, and heliophysics spacecraft are giving us a 3D movie of how an alien comet responds to our sun. And there's healthy, sharp criticism of over-interpretation. Blog posts and papers explicitly titled "Loeb's 3I/ATLAS anomalies explained" go through the data, point out where uncertainties are large, and remind everyone that extraordinary claims need extraordinary evidence. So where do I land? Speaking as a scientist, I think we should absolutely keep an open mind and test even wild hypotheses, but we should also be honest about what the data are actually saying. Every new observation of 3I/ATLAS so far has pushed it toward the weird but natural comet corner of parameter space, not toward engineered object. The OH radio lines, the evolving dust coma, the lack of narrowband artificial transmissions in deep Mir-KAT searches, all of these strengthen the natural scenario. The alien probe idea is, at this point, more of a philosophical prompt. It reminds us that interstellar probes are possible in principle, and that our instruments are finally sensitive enough that if someone else has built them, we might notice. But scientifically, the burden of proof lies firmly on those claiming technology, and 3I/ATLAS simply hasn't met that bar. In the end, I'd argue the real wonder of 3I/ATLAS is not that it might be a spaceship, but that it doesn't have to be. A natural comet from another star system, carrying exotic ices and dust grains shaped in a foreign protoplanetary disk, flying through our solar system once in a million years and leaving behind a trail of data. That's already an astonishing story. The alien hype will fade with the news cycle. The measurements we're making now will stay in the literature for decades, quietly reshaping our theories of how planets and comets form across the galaxy. That's a fun coincidence, but there's no causal mechanism behind it that we can currently justify physically. So when we say 3I/ATLAS keeps getting weirder, we're not saying it violates physics or that it's clearly artificial. What we mean is that every time we point a new instrument at it, we find it sitting at the edge of our expectations, more CO2 rich and water poor than typical comets, dust with unusual polarization signatures, gas and dust production rates that are high for its circumstances, chemical hints of odd metal and carbonyl chemistry, and an orbit and size that strain our population models for interstellar debris. None of those alone would force us to rewrite the textbooks, but together they tell us that planetary systems elsewhere in the galaxy can produce icy bodies that are cousins to our comets, not twins, and that our sample of 3 interstellar visitors is already rich enough to show us just how diverse that family can be.